Before I start, does anyone have any questions from last time? We're sort of basically through all the stuff on units and unit conversions. Uh, I'm going to do one more little thing, just talking about the prefixes, micro, milli, kilo, all that kind of thing. And then we're going to move on from that first set of practice problems and move on to the stuff on 1D kinematics. So almost already, but definitely after tonight, will be, I actually am writing smaller. Now I'm going to try to write bigger starting now. We're through all the material needed for the practice problems on units. So I would recommend getting to that as soon as you can, if you haven't started looking at those yet. And as much as you can, you want to do the problems without looking at the solutions. The solutions are there, and then just compare the solutions to your answer afterwards. It's because what you want to do is you want to see really clearly when you get stuff wrong, what was the idea that sort of mixed you up, and you want to make a mental note of that. And those are the things you want to fix, you know. And so if you're, and I know it's a thing people do a lot with these, but so if you approach it by looking at the problem and then looking at the solution and making sure it makes sense to you, it's hard to make those connections, you know, like where you're getting mixed up. And so what I would recommend is go through, once you've gone through all the notes, you feel pretty good about it up through tonight, then go through the practice problems, try to do them, compare to the solutions, then maybe go on to the next set of practice problems, and then a little bit later come back to the units practice problems and go through them again. You know, I'd say every practice problem you want to go through at least 2 times that way. Okay, and if you do that and you're like at each step in the practice problems, if you're thinking like, how do I know this? You know, just make sure you're not like memorizing the steps from the solution, but like, what is it that makes me make this decision in the problem at this point? If you get to that point with these problems, then the exams should not be a problem. Okay. Okay, so prefixes. There are a bunch of them. I'm only going to write down the most common ones. Micro, milli, centi, kilo, and mega. And micro, by the way, the symbols for these, anything with the Greek letter mu in front of a unit means micro. A lowercase m in front of a unit means milli. Lowercase c in front of a unit means centi. Lowercase k is kilo. And then mega is capital M. And you can think of these prefixes as actually just meaning, like, you can always just replace the prefix with a number. So for micro, anytime you see micro or see this micro symbol, just replace that with times 10 to the minus 6. Milli times 10 to the minus 3. Centi times 10 to the minus 2. Kilo is times 10 to the positive third, and mega is times 10 to the positive 6. And you can come up with the associated equalities that you can use in unit conversions. For example, 20, well, forget the 20. Let's just say, so 1 microsecond is equal to, replace the micro symbol with times 10 to the minus 6. And so this is equal to 1 times 10 to the minus 6 seconds. Okay? And that tells you that 1 microsecond over 1 times 10 to the minus 6 seconds is equal to 1. You know, the other ratio is equal to 1, 2. And this is something you can use in unit conversions, the same way, you know, we've done other unit conversions. Okay, so as an example, how many kilograms is, let's say, 50,000, you don't, let's see, kilograms, 50,000 megagrams. I've never heard of a megagram, but okay, so we're going to start with 50,000 megagrams, and we're going to do the conversions from here. So the way I'm going to do it is I'm first going to convert from megagrams to grams, and then I'm going to convert from grams to, no, I went the wrong, oh no, this is right. Okay, start with 50,000 megagrams, convert to grams, and then convert that to kilograms. Okay, we're trying to convert megagrams to kilograms. So 1 megagram is equal to 1 times 10 to the minus 6 grams. So at this point, if we multiply this number out, our answer would be in grams. Sorry, I messed that up too. I'm going to stop doing that. A megagram is times 10 to the positive 6. So this should be a positive 6. Sorry about that, but all you're doing is using these relationships. Mega is times 10 to the 6. Okay. And now I'm going to go from grams to kilograms. So 1 kilogram is 1 times 10 to the 3rd grams. The grams cancel. And you end up with 50,000 times 10 to the 3rd kilograms. And then if you wanted to put that in scientific notation, that would be, so 1, 2, 3, 4, so 5.0 times 10 to the 7th kilograms. Any questions about that? You could skip one step here if you just started. So you could start this by, instead of writing it as 50,000 megagrams, just replace the mega here with times 10 to the 6. Okay, And then all you have to do is convert grams to kilograms. So now you're at 1 kilogram is equal to 1 times 10 to the third grams, and you get the same thing. Yep.
So you're saying that if you mentioned about mega, it's equal to 1 multiplied 10 to the raised power 6.
That's right.
Grams.
Yeah, any units. Mega anything is times 10 to the 6 of the unit. You know, so mega meters would be times 10 to the 6 meters. And you can just always replace that prefix with whatever that factor is, that number. Yep. Any other questions about that? Here's another example. The fastest any object can move is the speed of light. Some objects can't even move that fast. And the speed of light is 3.00 times 10 to the 8th meters per second. So can any object move 150 kilometers per microsecond? So again, you can think of this as just a unit conversion. So we'll start out with 150 kilometers over microseconds. And I'm going to convert the kilometers to meters, the microseconds to seconds, and then we'll have numbers we can compare because they have the same units. So 1 kilometer is equal to 1 times 10 to the third meters. And so now our units of length are in meters. And then to convert the seconds, 1 microsecond is 1 times 10 to the minus 6 seconds. The seconds, the microseconds cancel. And we end up with 150 times 10. So now what's the exponent on the tens here? We have, in the numerator, we have a times 10 to the third. In the denominator, we have a times 10 to the minus 6. Positive 9, yep. Because you're taking, since the bases are the same, the tens are the same, you're taking the 3 here and subtracting the minus 6, which means you're adding positive 6. And so you end up with 150 times 10 to the 9 meters per second. That's bigger than 3 times 10 to the 8th. So that's faster than anything can move. Any questions about that? Okay, so that's the end of the stuff on units. And now we're going on to, in a way, you know, like units is just sort of necessary bookkeeping and stuff. The the next chapter is the first thing that's actually describing the motion of objects. So now we're getting into actual physics. So the first topic is kinematics of a particle in one dimension. And I want to just break down what each of these, the pieces of this title mean. So first, kinematics. Kinematics means that all you're doing is describing motion. You're not doing any calculations that involve the causes of motion. So you're not talking about forces. You're also not talking about masses. So the quantities that you're dealing with are things you could get from a videotape, okay? You could do all kinematics from watching videos of objects. You don't have to know their masses. You don't have to know how hard things are pushing on them. And mostly, we're going to be talking about relationships between position, velocity, and acceleration. Okay. So that's kinematics. Does anyone have a feel for what particle means? Yeah, that's right, exactly. It means that every object that we're describing, we're treating it like it only exists at a single point, and it's just, the point is moving around. So, no lengths. Well, let me write that a little more clearly. Let's say we're going to treat objects as if they have no length. There are going to be lengths, like objects are going to move from here to there, and we're going to measure those lengths. But the objects themselves, we're treating like they don't have any length. And one thing that comes about because we're not worrying about lengths is for something that just exists at a point, there's no up or down or left or right. So orientation doesn't matter. So all we're going to be talking about is objects moving from here to there. We're not going to be talking about objects spinning in place, okay? When we end up moving away from particle physics and start talking about bodies that actually have length, it is going to matter to us, you know, whether a person is on his head or on his feet, you know. Obviously, that's going to be important for some calculations. But for now, we're not going to deal with that. So this results in not having any orientations. And then the last thing, 1D, that just means that at any instant, the object that you're looking at only has two choices where to go, okay? You can think of it as forward or back, you know, side to side, where to go. Okay, so one 1D motion, the one that would occur to most people, like what path can something travel and be in one dimension? Along a line, that's one dimension, because a particle that's here can only go to the left or the right on that line, okay? One thing that, one path, one type of motion that may not occur to as many people is that is also a 1D motion. That's a little more like, this is a 1D motion because wherever an object is, it can only go this way or that way, right? It doesn't have any more than two choices, so it's 1D motion. Even though the path itself, in order to draw it, we need 2 dimensions. We're not worried about that. We're just worried about the fact that the object can only go this way or that way, okay? And because there are only 2 directions, in 1D motion, we can indicate any direction, like all the directional information we need can be treated with positive, negative signs, okay? Okay, so once we, so like in one of these 2 motions, all we have to do is say we're going to call the left, going to the left, positive, and we're going to call going to the right, negative. And once you make that definition, whether something moves positive or moves negative tells you everything you need to know about the direction of the motion, okay? In 1D motion, you can always indicate an object's position as a point on a number line once you make 2 choices, once you specify 2 things. And it's worth keeping in mind that these are arbitrary things, but they have to be specified in order to show an object's position using a number line, in order to put a number to the location of an object. 2 arbitrary, I'm just going to say things here. Okay, the first one of these arbitrary things is a location on the path to be called the 0 position. And the second one is the direction along the path to be called the positive direction. Okay, so for example, let's say, so these are train tracks rolling through the countryside. Here's the train, not touching the train tracks somehow. A very modern train. This is the only kind I know how to draw. Okay, so it's moving along the tracks. And we're going to treat this train as if it's a particle. So we have to choose some point on the train to represent the train. Let's choose, I'm just going to choose this location. Anyone know what that symbol means, by the way? Have you know that symbol? They, like for a while, for some reason, like all car companies did commercials that had crash test dummies in them. And they'd have this symbol all over them. That symbol indicates where the center of mass of something is. So like a crash test dummy has, you know, there's the head, and they have that symbol here indicating where the center of mass of the head is. And then they have the body with one of these indicating where the center of mass of the body is, and so on. And the reason that they do that is because the center of mass is a really important thing in doing physics. And so they'd watch a videotape, see what the acceleration and velocities of the parts of the body are, and they could do the physics because based on this, they can track where the center of mass is at every point. So there. So anyways, this is the center mass of the train. We're going to use that to indicate the location. And so right now, what's the position of the train? You can sort of, like, to try to kind of make sense intuitively out of that requirement that you specify those two things. Well, even though we know, even though we know that, say, this is 5 meters, you know, the problem isn't defining distances. We just don't have any reference point to assign a number to this, and we also don't know which direction from that reference point we're counting. Okay, but if I choose a point here and say this is what I'm going to call my 0 position, I'll write a scripty O for origin. Okay, so that so if I say that's the 0 position, and that's arbitrary, I could have made that over here. And then if I define a positive direction, let's say the positive direction is going that way. Okay, now I can count backwards. 1, 2, 3, 4, 5, 6, let's say 7 meters. The location of the train is, its position is -7 meters. Okay. And this isn't just some, like, this is sort of a mathematical explanation of something that makes sense to you, like in your daily speech, you know this is true. Like if someone asks you where St. Cloud is, it doesn't do any good if you say 500 miles, right? That doesn't help anyone. But if you say 500 miles north of Des Moines or whatever, you know, whatever is 500 miles south of, then what you've done is that makes sense now because you've defined that reference point. Essentially, you've defined the 0 position, and you've defined the direction. In that case, you did it by saying north. In our case, one dimension, you do it by saying positive. A positive direction is this way, negative is this way. Okay. And then once you define this, once you calculate this position, you can represent it on a number line. So there's the number line, there's 0. And so there's the location of the train, the position of the train. So notice, the first thing I want you to notice, all that other stuff I've said, I didn't care if you noticed it or not. But this is, okay, so I'll write these occasionally, and these are just sort of like, I think, helpful things to just kind of keep at the front of your head as you work through this. But notice that position has direction built into it. And that direction is given by the sign. Okay. When we get to 2 dimensions, a sign isn't going to be enough to give us a direction anymore, because, you know, if something has, this is kind of an aside, you don't have to write this down, but if something is, so say you set your 0 position, okay, and say you choose a positive direction to be this way. Well, what's this point? Is it positive or negative? You know, that's just not enough information to give you directions in 2D. You have too many options of directions to go. But in 1D, the plus minus sign is enough. One thing that we're going to always want to do, pretty much always, is we'll want to associate position with time. And often we'll represent motion, on a position versus time graph. Position so in order to do that, to associate a position with a time, you need to specify 3 arbitrary things. The first 2 are the same as they were before. So you need to choose where position is equal to 0, like a physical location that you're going to call position equals 0. Then you're going to have to choose a physical direction to be your positive direction. And the last one is you have to choose an instant that you're going to say corresponds to time equals 0. Okay. One way to think of these things is think of these 2 together as like laying down a ruler. Okay, like you can set a ruler down on the table with the beginning of the ruler starting over here or over here. Okay, I mean, if it's think of it as like a very long ruler. Your 0 could be here, your 0 could be here. You could hold it this way or flip it around and hold it the other way. But you have to actually choose where that ruler is to define a position. And think of the instant corresponding to time equals 0 as being when you turn the stopwatch on. Okay? And if you think of it that way, it's pretty obvious that these first two are independent of the third one, right? What you do with the ruler doesn't have anything to do with when you click the stopwatch on. So all three of these are arbitrary. So in the train example, imagine time equals 0 had been chosen, let's say 4 seconds before the snapshot that's shown, like the picture that I drew. Okay. Then what we would have for values is the position would be equal to -7 meters at time 4 seconds. Okay. Anyone have any questions about that? In other words, if you think of position as being a function of time, you can write this as the position at 4 seconds is equal to 7 meters. And on a position versus time graph, and these position versus time graphs, you're always going to have position on the y-axis, time on the x-axis, and you would plot this event. Yes, thank you. Yep. And so to plot that event on this position versus time graph, you'd go out to 4 seconds. And that would be that would reflect like that moment, okay? The train is at position -7 at time 4 seconds. And usually we're not going to be dealing with like individual events like this. We're going to be dealing with events where we know something about the motion as time goes by, okay? And if you know what the position looks like as time goes by, you end up with what you're used to as a mathematical function, you know? It has some curve to it, some shape to it. You can calculate slopes of it. You can, you can figure out where it crosses the axis. All those things that you've done with functions, we're going to do with position. Position being a function of time. Position being the dependent variable, and time being like free to move. Okay. One other thing to notice. So the first one that I said was notice that position has direction. It can be positive or negative. We are never going to use negative times. Mathematically, you really could use negative times, but in physics, we don't do that. And so we're never going to have to define positive time directions. You know, time just marches forward, and that's the way we treat it. Okay. Okay, so now, So we talked about what position means in 1D. And you know that you have to make those arbitrary choices to figure out the position. We talked about the relationship between position and time. And now I'm going to go into the other kinematic quantities. And I'm going to define those in terms of position and time. And I want to keep straight as we do this that some of these quantities are going to have directions associated with them and some are not. Okay, really the ones that are going to be important to us are always going to have directions associated with them, but the ones we tend to use in everyday speech don't. And so that's why I want to make this distinction. So let me just start by making this table. So directional kinematic quantities. And non-directional kinematic quantities. Okay, so we talked about position already. And the first thing I'm going to define is a quantity that's very closely related to position. That's displacement. It has an E in there, but I couldn't fit it. Displacement has sort of like a non-directional analogous quantity, which is distance. Distance and displacement are kind of both trying to get at the same information. Just one includes directional information, one doesn't. The second kinematic quantity I'm going to define is velocity. Velocity has direction built into it, so it can be plus or minus. And the related non-directional quantity that we tend to use more in speech is speed. And then the third one, it doesn't really have a non-directional analog, but acceleration. So these are more important for physics. But I want to talk about like how these relate to distance and speed, because these are how we're used to talking. And I guess because we're used to using these in speech, a lot of problems, like the way the problems are worded, use distance and speed, and you have to sort of tease out the directional quantities out of it. Okay. All right, so the first one I want to define is displacement. So choose two instants T1 and T2. You know, that could be like 1 second and 5 seconds, or 12 seconds and 100 seconds, or whatever. But you have to choose those two. Then the displacement from T1 to T2 is the position at T2 minus the position at T1. Let's call this equation 1. So this is like the first big equation that we're going to come back to over and over again. And notice that I'm using this function notation here. I'm not talking about position times t2 and position times t1. I'm talking about the position at that instant and the position at the instant t1. Okay, so let me give you sort of a typical example. So let's say time is in seconds, position is in meters. And let's say that an object starts here, and then, so at 0 seconds, the object is at 1 meter. 1 second later, it's at position 2 meters. 1 second later, it's at position -1 meters. And then 1 second later, it's back at 0 meters. So it follows a path like that. Okay. So first of all, thinking about those three arbitrary things that you have to choose, have those already been chosen, or do we have to choose them? Like, how do we know that they've been chosen? They have been, yeah. Nothing can, you can't assign numbers to the position until you choose those two position values, and you can't assign positions to times until you choose the time equals 0. So anytime you're given a position at a time, or you see a graph of position versus time, those arbitrary things have already been chosen for you. Okay. All right. So first, let's figure out what's the object's displacement between time equals 1 second and time equals 2 seconds. And then the second thing we're going to do is what's the displacement between time equals 0 seconds and time equals 3 seconds. Okay, so for part A, for both of these, I mean, we're just going to figure out what the position is at each of these two instants that are defined and do that subtraction. So for part A, the displacement is, what's the position at 2 seconds? Here's 2 seconds, so the position is -1 meter. And then we're going to subtract the position at 1 second. What's the position at 1 second? Yep. And so -1 minus 2, we get a displacement of -3 meters. And the negative tells you the direction that the thing is moving. This object is moving in the negative direction over that time interval. Okay. Now to do the same thing for the two different times, what's the position at 3 seconds? Yep, 0. What's the position at 0 seconds? Yep, +1 meter. And so the displacement is -1 meter. Any questions about those? Yep.
I don't understand how that's -1 meter.
0 minus 1, or the second.
How you got the meters
Off the graph, yeah. So the times that we care about are 3 seconds and 0 seconds. So at 3 seconds, we're just looking for where the graph crosses the 3 seconds. At 0 seconds, we're looking for where the graph crosses 0 seconds. So at 3 seconds, it's crossing. It's actually, these are the two that are probably the least clear. Let's do it for 2 and 1, okay? Like in A. So at 2 seconds, we're looking for where the graph, like think of this dotted line as, that's the 2 second line. We're looking for where the graph crosses it, and it crosses at -1 meter.
Okay.
And,
Yeah, I see.
okay, yep. So that's what we're doing. This one, at 1 second, the 1 second crosses the graph at +2 meters. So that's it. Right. Any other questions? Okay, so let me talk about, like I said, distance isn't something that's going to come up really in this class. But let me talk about how you would calculate the distance. So break up the path into, I'll call them legs, like legs of the journey. And these legs are just all of the times that the object keeps moving in the same direction. When it turns around and goes the other direction, that starts a new leg, okay? And once you've broken it up into these legs, the distance is equal to the absolute value of the displacement of leg 1 plus the absolute value of the displacement of leg 2. Okay. So what this means is if between your time 1 and your time 2, if the object doesn't change directions, then distance is just the absolute value of displacement. Then it's easy. If it does change directions, then you have to figure out the displacement between each direction change, take the absolute value of that, and add them all up. So let me do these same two examples to calculate the distance. So C, let's calculate the distance between time equals 1 second and time equals 2 seconds. And then let's calculate the distance from time equals 0 seconds and time equals 3 seconds. Okay, so for C, we have to look at the graph and figure out if between 1 second and 2 seconds, if this thing ever changes direction. So between this point and this point, the object is just steadily moving down, right? It's not really down, but it's steadily moving in the negative direction. Okay? It never turns around and starts going in the positive direction. So this is a case where there's only one leg of the journey. And so the distance is just going to be the absolute value of the displacement. So the distance is equal to the absolute value of the displacement we already calculated, which was -3. And so you just get 3 meters. We calculated that as part A. Okay, so now let's do the one between 0 seconds and 3 seconds. So between 0 seconds and 3 seconds, it starts out going in the positive direction, right? It's heading up. Then it turns around and goes down in the negative direction, and then it goes up again. So we have 3 different legs of this journey, okay? And so you can do it all, like calculate all the displacements, or you can just recognize that it's going 1 meter here, then it's going 1, 2, 3 meters in the second leg, and then it's going 1 meter in the third leg. You're just calculating like the vertical distance that's traveled in each of those legs and then adding them up. Okay, so 1 meter up to get to here, 3 meters down to get to here, 1 meter up to get here. And so you get a distance that's equal to 1 plus 3 plus 1, 5 meters. Any questions about that? Yep.
So number 3.
Yeah.
So the second leg is going negative. Whatever you put, like -3.
Yeah, I suppose that's what I would put here. Yeah. So that's exactly right. So if you think of each of these as the absolute value of the displacement of that leg, then yeah, this should have a -3. Yeah, that's right.
So instead of 5, is that going to be?
It doesn't change it because this is an absolute value. So that means you drop any negatives. So you just keep adding it up. So what distance does, you know, like if you drive to Iowa City and back, you know, it's, I don't know how far it is. Why do I keep picking these cities? I don't know distances for. Say it's 300, 400, 300 miles to get to Iowa City, okay? And then you turn around and go the opposite direction to get back, right? Your distance is 300 plus 300. So your distance traveled is 600. You know that because distance is what you use in everyday language. Your displacement, though, over that whole trip is 0 because you started in a location, let's call that position 0. You went somewhere, came right back to 0 position. 0 minus 0 is 0. Okay? So displacement takes the direction stuff into account. The fact that you negated the trip that you just did is reflected in the displacement. With distance, though, it doesn't work that way. The fact that you went one way and then negated that trip that you just took, those both get added on as positive. Your odometer doesn't go back to 0. Your odometer says you went 600 miles. That's a distance measurement. Any more questions? Have you guys seen Ferris Bueller's Day Off? You know, like when he has his dad's expensive car, whatever his Cameron has his dad's expensive car, and so they put all these miles on it. So their scheme is to put it up on blocks, put it in reverse, and run all the miles off the car. You know. Well, that would work in a sense. He was hoping that odometer measured displacement in a way, you know, in sort of a roundabout way. But he was hoping that he could make the car think he was negating the trip he just took and it would go back to 0. But that's not how that odometer works. It's hard to believe any odometers work that way, but maybe. Okay, so that's it for displacement and distance. So now let's talk about velocity. And remember, actually, go up here for a second. Where is it? To where I defined displacement. Change this title to displacement and distance. Like I just want you to keep in mind that distance is like a relative of displacement. Just one has direction built in, one doesn't. So now we're going on to velocity, and its relative is speed. And there are two types of velocity that I'm going to introduce. One is average velocity. And one is instantaneous velocity. And this average velocity isn't really going to be any use to us in the class, except as a way to introduce how you calculate instantaneous velocity, or to define instantaneous velocity. So this is the one that's going to be more important. Okay. And so like later in the class, whenever I talk about velocity, I'm going to remind you of this again later, but if I just say velocity, I'm always going to be talking about instantaneous velocity. The only way I'll talk about average velocity is if I specify average velocity. But the average velocity from time t1 to time t2 is defined by this equation. V average is equal to the position at t2 minus the position at t1 divided by t2 minus t1. I'm going to call this equation 2. And if you look at this equation, notice that the position at T2 minus the position at T1, that's the definition of displacement. So you can think of this as the displacement divided by the elapsed time, the change in time. Also, on a position versus time graph, the average velocity is the slope from T1 to T2. So if you know that an object's motion looks like this, and say this is your time t1, and this is your time t2, so then this is your position at time 2, this is your position at time 1. The average velocity from this instant to this instant is the slope of that line. Maybe here's another color. Okay, so calculus comes into physics in a few places, and this is one of the important ones because Calc 1 is all about calculating slopes of functions. And this, like basically anytime you hear the word slope in this class, that's a time that calculus is useful, you know, in physics. And we're not going to do problems where you have to do calculus, obviously, but it is, I think, useful for understanding this to keep in mind where calculating those slopes using calculus is, you know, would come into it. Okay, so I said that if you drive from here to Iowa City and back, what's your displacement? 0. So what's your average velocity? 0. Like if it takes you 7 hours, right? Your displacement is 0. So your average velocity is the displacement 0 divided by 7 hours, which is still 0. So who can calculate the fastest average velocity in the history of NASCAR? Right, exactly. So as long as you start and stop at the same point, as long as T1, T2, your positions are the same point, then your average velocity is always going to be 0. Okay?
How would that average velocity look like that? Would it just be...
Yeah. Okay, so... Yeah, that's a good question. So your trip to Iowa City and back would look something like this. Okay, and your this would be your time T1, this would be your time T2. Your average velocity would be the slope of this line, and that line has 0 slope. And all the stuff you did in between doesn't matter. All that matters is those 2 points that you chose, those 2 instants. The NASCAR race would look like it would look like
Will it look like this? Up and then down?
so it's a little, yeah, it's a little so if you think of, it's a little hard to do it in one dimension like that and still, but think of it this way. Whoops. I need to make it end here though. Okay, so each one of these blips represents 1 lap. And so here's 1 lap, 2, 3. This is a really short NASCAR race, but there would be T1, there would be T2, and the average velocity would be the slope of that line, which is 0. The average distance sorry, we already talked about distance. The average speed is just equal to the distance divided by the elapsed time. Or you can think of that as, you know, distance divided by T2 minus T1. Can average speed ever be negative? It can't, because distance is always positive. Remember, because it was made up of absolute values, and the elapsed time is always positive. So all you do with distance is just keep adding to it. the fact that it's always positive says that there's no direction associated with distance, with speed or distance. Any questions about that? Yep.
You can never go at negative speed. Pretty sure it stops at 0.
Yeah, that's true. Based on observation.
Right,
Yeah,
yeah.
right. But you can go a negative velocity.
Right.
Let's stop there, and next time I'll define instantaneous velocity. Okay, any questions before we go? Today's Wednesday, right? So Monday we have our first lab, the people who have Monday lab. So it's going to be worth the wait.